Okay, here's some examples on law of conservation of mechanical energy. Okay, or like the energy theorem, which we'll be doing our next assignment on. So the law of conservation of mechanical energy states that that is a frictionless system, or in a frictionless system, all mechanical energy is conserved. Okay, and so we're going to do some problems kind of looking at that. So in this case here, we have a heavy object is dropped from a vertical distance of 12 meters. What is the speed of the object when it hits the ground? Okay, and so again, always start, write down what we have. So we have heavy object. We don't have a mass. Mass is unknown. Okay, we'll talk about that in a little bit. Okay, the vertical distance is 12 meters, and whenever something is being dropped, it's falling at gravity 9.81 meters per second squared. Okay, we want to know the speed. Okay, and so basically, again, like if we think of something falling off a cliff, okay, at this top point here, we have potential energy. Okay, at the bottom point here, all of that potential energy is converted into kinetic energy. Okay, and we know that for mechanical energy is equal to kinetic energy plus potential energy. Okay, at this top point here, the EM and EP would be equal. Okay, because the total amount of energy is at this point when it's not moving yet is all just potential. Therefore, we know that like at the bottom point, all of that mechanical energy has to be kinetic energy. So really what we're seeing at the top, we have EP. At the bottom, we have EK. So EP, or potential energy, is going to equal our kinetic energy. Okay, our potential energy formula, mgh, is equal to 1/2 mv squared. Okay, we want to solve for V. We don't have M, but we have G and H. So we can rearrange this formula to then solve for V. So if we're rearranging it, we'll divide both sides by M, and my M's all cancel. That's why we don't need the mass in that initial, like it doesn't matter, we don't need it. Okay, so now we have GH is equal to 1/2 V squared. Okay, we're going to times both sides by 2 to get rid of this. So we have, over here, 2GH is equal to V squared. We'll square root both sides to get rid of the squared. So we get V is equal to the square root of 2GH. Okay, that's a good formula to kind of add to your formula sheet. You'll be using it a lot whenever you're given a height and then you're asked to find like its maximum speed. Okay, so now put our numbers in. So 2 times 9.81 meters per second squared times 12.0 meters. Okay, and if we're thinking about like unit analysis, we'd have our meters squared over seconds squared, and then since we're square rooting them, we get meters per second. Okay, put it in a standard calculator, and we get 15.3 meters per second. So that would be its maximum speed when it hits the ground. Okay, here's another example. This one's a little bit more complicated. So we have an object is thrown vertically from the top of a 100-meter building. So they're throwing the object down off the building, okay, with a speed of 10 meters per second. What is the speed when it reaches the ground? So again, we have this building here. Okay, this object is being thrown off the building. Okay, its initial speed, so it's VI, is equal to 10.0 meters per second. Okay, we want to know like its final speed when it hits the ground. So VF, that's our unknown speed. Okay, and for this one, well, I guess there's a couple different ways that we can do it. But we're going to use the mechanical energy formula to do this. So basically, like if you look on your formula sheet, Okay, potential energy initial plus kinetic energy initial is equal to potential energy final plus kinetic energy final. Okay, we have initial potential energy. It's up, raised up to a certain height. So we know that we have this. Okay, we have kinetic energy because it's thrown down. So we have some initial kinetic energy. Our final potential energy, when this hits the ground here, there is no potential energy. So this is equal to 0. So we can kind of get rid of that. And then we have our final potential energy, or kinetic energy, which would give us kind of our final speed here. So we can put our formulas in. So this is mgh plus 1/2 mv, this is our vi squared, is equal to 1/2 mvf squared. Okay, we can divide everything by m because it's in every formula, so that gets rid of our masses. So we got gh plus 1/2 vi squared is equal to 1/2 vf squared. Okay, put our numbers in. So we got 9.81 meters per second squared times the height, 100-meter building. We're going to plus 1/2. Our VI is 10. That's squared. That's going to equal 1/2 VF squared. So we put our numbers in. This side altogether equals 1,031, okay, which is equal to 1/2 VF squared. We're going to times both sides by 2 to get rid of this. Okay, and then we'll square root both sides to get rid of that. So we got VF is equal to the square root of 2 times 1,031. And our VF is equal to 45.4 meters per second. Okay, so that's using our mechanical energy formulas. Okay, basically our initial mechanical energy has to equal our final mechanical energy, or our overall energy can't change is really what we're looking at here. Okay, you could use if you have VF, you have VI, or you're looking for VF, you have VI, you have gravity, you have distance. If you want to, you could use your kinematics formula, VF squared equals VI squared plus 2AD, and it'll give you the same number. Okay, if you won't have to worry about showing work, so really either way works, but for mechanical energy, this is usually the one we want to use to show that that change in energy and how it works. Okay, if you have any more questions or you want me to do more examples, okay, just let me know. If you're looking at a textbook question, you're like, I don't get how to do that. I can do it here on this sheet of paper, just like these examples here, and show you how to do it, or do it up on my whiteboard. Okay, just let me know what you need to see.